So we have talked about this idea that there could be situations where we have infinitely many statements. In particular, when we have these summation formulas where we say, hey, the sum of these integers can actually be reduced to this really quick computation, and you actually don't need to add anything up. You can just plug your end number into this formula, and it will tell you what the sum is going to be. So let's think about this analogy of dominoes. Okay, so in our case, if we go back to the statement that the sum of integers starting at 1 and going up to n, so from I equals 1 to n, the sum of these i's, 1 plus 2 plus 3 if n equals 3, 1 plus 2 plus 3 plus 4 all the way up to 100 if n equals 100, etc. Let's think about each of these dominoes. Imagine you stack a bunch of dominoes in a row. And you call this domino, or let this kind of physically represent p of 1. This one would be p of 2. So p of 1 in our situation would be that the sum beginning at 1 and ending at 1. So that's basically just the term 1 with nothing added to it. But that would give us the same answer as taking 1 times 1 plus 1 over 2. And okay, well, the left side is 1. 1 times 2 divided by 2 is also 1, so they are equal. P of 2 would be the statement that the sum from I equals 1 to 2 of I would equal 2 times 2 plus 1. Then there'd be P of 3, and so on, right? The idea here is that we would have infinitely many dominoes stacked in a row. Now, one way to knock over all the dominoes in the sequence would be to tip each one by one until you tipped infinitely many of them over. That is impossible. You'd probably get tired after a while. Another way to do it would be to set your dominoes up so that the dominoes are close enough such that when you knock one domino over, it hits the next domino, which tips over, hits the next domino, and creates a chain reaction. So we're actually going to try to do that here. That analogy will apply perfectly to what we're doing here. We need to figure out a way to where we could sort of automate the knockdown of these dominoes. And what I mean by knocking down the dominoes in the context of mathematical statements is proving that they are true. So when I say knock down a domino, that means prove that that particular statement is true. So what would have to take place for me in terms of dominoes to make sure that I can knock the whole sequence over? Well, first of all, you have to initiate the sequence, right? So I have to initiate the collapse. I would have to tip this one over first, right? But now, what guarantees that next domino, or that domino knocks over the next domino? Well, I could just observe it, right? And see if that knocks over the domino. But maybe that only gets me to P of 2, and I've knocked down P1, P2. But what about the rest of them? How do I ensure that the dominoes all fall over? Well, one way to imagine that is let's focus on kind of over what's going on here. So let's imagine that I can establish, or I can convince myself that anytime I tip a domino, we'll just call this P of k, just to be as generic as possible, that if I activate P of k, that I can guarantee that essentially this spacing between these two dominoes is always going to be just right, and that's always going to tip over the next domino. So we need to establish every domino knocks over or knocks down the next domino. So I have to prove that, but then just because I know, if I tell you, hey, yeah, I promise you every domino knocks over the next domino, well, somebody's got to initiate the sequence, right? So here we have to initiate sequence. I'll just write it like that. Okay, and so because I know every domino knocks over the next domino, and I initiate the sequence, well, that means that P of 1 is going to fall down, which means it's going to knock over P of 2, because every domino knocks over the next one, I'm sure of that. And then P of 2 knocks over P of 3, which knocks over P of 4, etc., etc., etc. Now, the one confusing kind of part here for a lot of us when we first see this is, well, what does P of k mean? The idea of using k in place of n, remember n is a set of potential values. In our situation, it starts at 1, and it can go as high up as a positive integer as it wants. Okay, so what we're saying when n equals k, okay, again, remember, n is a variable, n can vary. But when we say n is equal to k, it's as if we're kind of isolating or we're pinpointing a very specific domino in that sequence. We're just not saying which one it is because we want it to be very general. So we are going to basically have to create this burden of proof on us to show that every domino knocks over the next one. And we'll see how that works pretty soon. Let's make that a little bit more mathematical. Take everything we just said in terms of dominoes and now apply it to mathematical statements. So step 1, this is what we called initiate the sequence. That's step 1. And then steps 2 and 3, okay, let's read through this for a second. Prove what we call the base case is true. So in other words, prove your first statement. What's the smallest possible statement in the context of the problem? Well, for us, this value of n0 is equal to 1 because that's the smallest that n could be. But as another kind of side example, let's just say we have another statement that says the sum from I equals 5 to n. Well, in that case, your n naught would equal 5 because n can't be 4. You can't sum backwards. You can only sum up from where you are. So that just depends on the statement. Your base case is going to be determined by, if it's a summation problem, where your summations start. What's the smallest possible statement that you could have? You can't do P of 1 because then the sum would go from I equals 5 to 1. And this has to be greater than or equal to n naught. So it can equal n naught, which would just give you the one term, but it can't be greater than or equal to it. Okay, and this is what we call the every domino knocks down the next domino. Every domino knocks down next domino. And the idea here is that we are going to do this assume step. Okay, the assume step is often called the induction hypothesis. It's a hypothesis. We're going to assume that the statement P of k is true. So in the context of what we were working with, we would just say that assume that the sum from I equals 1 to this value, this fixed value, n equals k, of the first k integers, assume that that would be, well, okay, we notice that it's always the max value times the max value plus 1 over 2 in our formula. We get to assume that. If you're like, well, how can you assume something you're trying to prove? The idea here is that we're just using this to prove that if this domino can be tipped over, that it will always tip over the next one. Now, the good news is that we already know one domino can be tipped over. That's our initiate sequence step. We've already knocked that one over. We proved that one first. But this statement makes it general to say that, okay, if every domino knocks over the next one, then P of 1 knocks over P of 2, which knocks over P of 3, which knocks over P of 4, etc. So this is still a burden of proof on us. We just have to establish that if one domino can be knocked over, that it always knocks the next one over. And that's why we keep this generic value n equals k. So in the next video, we'll actually take a look at our first induction proof for these summations.